and 46. So f of t equals 1 minus hyperbolic sine over 1 plus, no, the top is plus, the bottom is minus. 1 minus hyperbolic sine t. Perfect, excellent. Good. So let's differentiate this. So I have f prime of t, but I know that I have to use the quotient rule. Anyone would like to give us the quotient rule?
So it's the top function, the
Yes.
derivative of top function is cos.
Yes, good. Times the denominator. Then minus. Copy the top.
1 plus sine t
Times this
cos.
prime. So it will be cosine, but with minus. So I'm going to change this. And I have hyperbolic cosine t over this squared. When I graded your homework, someone put this term in front and this term in the back. So be very careful. If you keep it always as 1, 2, I think you're not going to forget. So 1 prime times 2 minus 1 times 2 prime. Because you always have 1, 2, 1, 2. But if you want to twist it, I'm fine. So let's try and simplify. But as you see, we have a cosine, hyperbolic cosine in both terms. I'm going to pull that out. 1 minus hyperbolic sine squared. So then I have 1 minus sine, 1 minus hyperbolic sine, plus 1 plus hyperbolic sine, right? So these two will go away. Let's write them. 1 minus hyperbolic plus 1 plus hyperbolic sine. These two will go away. So there is a 1 plus a 1. So this will be 2 hyperbolic sine, hyperbolic cosine t over 1 minus hyperbolic sine squared t. Any questions? Any questions on this? Anything else? Would we like to choose another?
Can you do number 40?
42.
42 and 40. Let me copy them. So f of t, natural log of hyperbolic sine, and you said 42. Age of x equals e to hyperbolic tangent x. No, it's 2x. Okay, perfect. We'll replace it back with v. It's just easier for me to write and for you to see. So f prime. I need to differentiate natural log. How do I differentiate natural log? What do I have to write?
1 over the function?
Yes. Times
the function prime.
Times the function prime. Perfect. So I have hyperbolic. Good. How much is hyperbolic sine?
That is hyperbolic cosine.
And how much is hyperbolic cosine over hyperbolic sine?
That would be cotangent.
Very good. Done. 42. So h of x, I'm going to copy it, equals e raised to tangent, hyperbolic tangent 2x. When we differentiate e to a function, what do we get? What is the formula we have to, or the rule that we have to apply here? Anyone?
Function times the prime of the
Yes, e to the function times the function prime. Perfect. Good, so let's continue. So then h prime will be e raised to hyperbolic tangent times hyperbolic tangent prime, which is
hyperbolic sine over hyperbolic cosine.
hyperbolic, so hyperbolic tangent is,
Oh yeah, sorry, secant. Hyperbolic
no worries,
secant.
no
Right, I
worries,
see it.
of the argument times the inner function prime. That's why I covered it, because it's not plain x, and I don't want to forget. So times this prime, which is 2. You can rearrange it if you want to. All you have to do is just put 2 in front, and that's it. Not to be understood that this is 2x times 2. No, 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 no. This is separate and 2 will be in front. So now you have all the information that you need to complete the derivatives assessment. Please start working on it as soon as possible. It has like 2 or 3 pages. It's not long, but now you finally have all the information you need. I wanted to go back to one example, and then we'll start related rate. Applications before related rates. So I'm looking to see which section that is that I need to go back to. Yes, I found it. Section 3.5. One item left over because I wanted to finish everything you needed for this assessment. Okay. And I would like to talk about orthogonal trajectories. One example. Where are they? Right here. Okay, orthogonal trajectories. We're going to choose an example, and then I'll come back. So, what are they? So, let's say we have families of functions. So, I have these families of functions, or these are circles. They're not functions, they're curves. So, in my example, these are not functions. They're just circles. They are curves. Okay. And let's say we have another family of functions that are represented by lines. Now you notice something very interesting. At each and every point of intersection, everywhere, the tangent to one and the tangent to the other are perpendicular. At any point of intersection. If I can show that at any point of intersection, the tangents to one and the tangent to the other, this is a line, it's the tangent itself, right, are perpendicular, then we say that these are orthogonal trajectories of each other. And I'd like to illustrate with one example. Let's look at the 53. X squared plus y squared equals r squared. Can anyone tell us what is that? And then ax plus by equals 0. Can anyone tell us what this is?
Area of a circle.
Very good. It is a circle. Can anyone tell us what this is? Of course, a line that passes through the origin. But because R can be anything, this is a family of curves. If this is 1, I have this circle. If this is 4, I have this circle. If this is 9, I have this circle, and so on and so forth. This is a family of circles because this can be anything, of course, positive number. Here, the slope, right? So B will be, so by equals negative ax, or y equals negative a over bx. I solved this equation for y. I moved ax to the other side, and I divided by b. So this is the slope. But they all pass through the origin. Okay, so the question is asking us, show whether these are, or investigate whether they are orthogonal trajectories of each other. So what I recommend is, number 1, find the points of intersection. Find points of intersection. How do I find the points of intersection? Where they intersect. How do I find that? I have 2 equations. I want to know if they ever intersect. If they don't intersect, I don't have anything to discuss.
Set them equal to each other.
Yes. In other words, not set them equal to each other, but solve, right? So if I had 0 here, I would have set them equal to each other, but I can't, right? But I have to solve. I can solve the second equation for y, which I already did, and plug it in the first equation. So then I have x squared plus, I have this, a squared over b squared, x squared equals r squared. So what I did, I solved the second equation for y, and I replaced the y value now that depends on x and some numbers in the first equation. Now you can see this is a constant, this is a constant, so I will be solving for x squared. How do I solve for x squared? What will be the next step? I want to solve for x squared. What do I have to do next? Can I combine like terms, or I have another way?
Factor out the x squared.
Very good, of course. And I will find the least common denominator. Let me write it like this first so you can see it. But of course, the least common denominator is b squared, so I have b squared plus a squared over b squared. Or in the correct order, x squared times a squared plus b squared over b squared equals r squared. From here, how do I solve for x squared? Can anyone tell us how to solve for x squared? What should I do to both sides to solve for x squared?
Subtract r squared.
Say it again.
Subtract r squared. Wait.
Flip the a squared plus b squared over b
Very
squared.
good, very good. So b squared r squared over a squared plus b squared. Do we agree with this? So since this is quadratic, how many solutions do I have to write?
2.
Yes. And I have to write plus or minus. BR, because I take the square root, over the square root of a squared plus b squared. Don't touch that. You cannot simplify that. So it appears that the circle is crossed by this line, normally in 2 points. I'm going to call point A and point B. Here is BR over the square root of a squared plus b squared, but this is negative BR over the square root of a squared plus b squared. Notice that I have not determined the y value yet, y coordinate yet. I have x. But look what I know. I know that y equals negative a over b times x. So y equals negative a over b times this. When it's positive, I have br over the square root of a squared plus b squared, or with the other sign, the negative, but that will change this into positive, a over b, br over the square root of a squared plus b squared. Simplify, simplify. So the first one is negative ar over the square root, and the second one is ar over the square root. So these are the values of the y coordinates. So this goes up here, minus ar over the square root of a squared plus b squared, and this is ar over the square root of a squared plus b squared. So I found that these are points of intersection. Fine. In step number 2, I have to find the slope dy over dx for the first curve and dy over dx for the second curve. So x squared plus y squared equals r squared. Differentiate implicitly to determine this. What do I have on the left-hand side?